You will let me know when to start, or we are already
Yes, ma'am.
in
I'll
the
be introducing you. After that, you may start your presentation.
Okay.
Good evening. Warm greetings, Dr. Mozhdeh Shahbazi, and good evening to all the online participants present here. We start with another keynote session with Dr. Shahbazi. She is an assistant professor in the Department of Geomatics Engineering, the University of Calgary, since 2016. She received her BSc degree in civil engineering in 2009, her MSc degree in geomatics engineering in 2011, and her PhD in applied geomatics in 2016. She is an adjunct member to the graduate program in Earth and Space Science and Engineering at York University, and also a secretary of Working Group 2, TC1 at ISPRS and Director in the Executive Board of Canadian Remote Sensing Society. Her current research areas include development, integration, and calibration of ranging and imaging technologies for unmanned aerial vehicles and autonomous mapping via vision-guided unmanned aerial systems. The focus of the technologies developed in her lab is on high-precision mapping in three critical contexts. First, surveying and metric inspection of urban infrastructures such as telecom towers, buildings, power lines, and railways. Second is monitoring open pit and underground mining sites. And third, smart farming and precision agriculture. Today, she'll be delivering her talk on the title, Autonomous Systems and Geospatial Visual Intelligence. Up to you, ma'am.
Thank you for the introduction. So hello, everyone. I think good afternoon, India time, and good morning, Canada time. So thank you again for inviting me as a keynote speaker to this very nice conference. I've personally enjoyed all the talks so far, specifically the keynote lectures. It's an honor to be alongside such speakers. Well, as introduced, I'm Mozhdeh Shahbazi, and I have currently two positions. I'm assistant professor at University of Calgary, director of Autonomous Mapping Lab, and I'm also lead scientist and science manager at another college research center, Center of Geomatics of Quebec. And I basically manage the Technology Access Center there, which is focused on photogrammetry and computer vision. So my talk today will be about autonomous mapping and visual intelligence. Well, they already introduced me. So yeah, I got my BSc in civil engineering with a major in surveying in 2019. And then I continued my master program in photogrammetry engineering till 2011. I was at the same time working as a survey engineer in a consulting company. And then after that, I moved to Canada. I started my PhD in applied geomatics. I was at the same time working as a research assistant at York University. Mostly my work was focused on computer vision. And also I was working as a part-time geospatial data analyst in Center of Geomatics of Quebec. So after that, I joined the University of Calgary as an assistant professor in 2016. Here are a few members of my lab, the Autonomous Mapping Lab. Right now, I'm in the middle of deciding whether I want to stay in that type of academia on the research base, or I want to more do industrial research type. And that's why I've been on a leave from University of Calgary, and I've been working as lead scientist first, and now as a science manager in a more industry-based research center, still affiliated with college. So it has that combination of academia and industry that I'm experiencing right now. So it's called Center of Geomatics of Quebec. It's, of course, as the name says, is located in Quebec, Canada. It's a college center for technology transfer, if I want to just do a translation from French to English. And basically, we are the only center in Canada specialized in photogrammetry, and our mission is basically bringing all the geomatics and geospatial innovations to companies and to specifically small and medium-sized enterprises. So enough about me and my career path. I just thought that would be inspiring maybe for some early career researchers like myself who are still exploring what best fits them. So let's talk about autonomous mapping and what it takes. Of course, first of all, we have to be able to perceive our environment and be able to interact with it intelligently, and to be able to perform the mapping missions. And then to perceive, of course, we need sensors, and these sensors don't move by themselves, so we need platforms. Whether it's based on a terrestrial platform, whether it's a vehicle or even a backpack system, or flying manned or unmanned vehicles, so aircraft or drones, we need those platforms. And I'm going to focus mostly in this presentation on those platforms that are based on drones. So as I said, the first thing we need is sensors to perceive. So a good chunk of my job is actually sensor integration, making sure that as many as sensors are needed for collecting all types of information are there and they can be working together. Synchronization is, of course, one of the most important issues with all the sensor integration jobs. And then for most applications on drones, we do need real-time data collection and real-time data processing sometimes too. So what kind of processor we will use and so on is all questions we have to ask. So one of the advantages of the place that I'm currently working in is having access to quite a unique laboratory of equipment, pretty much unique, I would say, across Canada. We have different sensors from industrial laser trackers to that actually we are now using for collecting ground truth of autonomous drones. Hyperspectral cameras, whether small ones that can go on drone or large ones for going on aircraft. Different types of scanners, whether they are small size again for going on drones or terrestrial scanners and mobile laser scanners. Different types of cameras, multispectral, optical, thermal cameras, and so on. So that's what I would call my sensor paradise, because that's where the whole work actually starts. So here is a few examples of sensors that we integrate. Like what we can see right now on the left of the screen is a sensor combination of maybe 5 plus 3, 8 cameras in there, plus GPS INS. At the right side, it's a simple LiDAR camera INS integration. So platforms that we work on, of course, most of them are drones, but we also work on like manned helicopter and manned aircraft as well. We're not really involved in like manufacturing or building platform, just integrating new sensors on them and being able to apply them in new contexts. So as we already heard from the previous keynote speaker, a big chunk of the work of sensor integration actually is sensor and system calibration. So different setups are needed really for different types of sensors, whether we are working with cameras, with laser scanners, with GPS INS, for example. And it's very important to actually choose the right physical models when we are working with different types of sensors. So maybe some of you are familiar with this camera that I show here. This is a ladybug camera. It's a combination of 6 cameras to get like a 360 view of the environment, used both on drones and on mainly mobile mapping systems. So here is a sample image we've taken with it in our calibration room. So maybe one question I'd like to ask, and I give you a minute just to think about it, whether this camera, in your opinion, is a fisheye camera or a wide angle camera? So it's very difficult to say, because if we see, okay, they're really, well, the field of view is quite large, and then there are really large lens distortions visited on these images. And then what the company advertises is that this is just a wide angle camera that can be And the model they provide for its calibration is just adding basically polynomial coefficients to the radial lens distortion component of the calibration. But we found that it's actually a fisheye camera. It means it's not following a central perspective geometry and a fisheye geometry actually. So here is our errors after calibrating. So based on the radial distance of the pixels from the center of the image, we plot the residuals after the calibration. So we did two models of calibration, one with a central perspective model with 5 coefficients for the radial component as the manufacturer suggests. So just assuming that this is a wide angle, it has just wide angle lens, and the other one is using the real equidistance fisheye model. And so projection of the fisheye model. So we can see that actually the errors are quite uniform. They're not increasing with the radial distance if we use the fisheye model, but we can see that the errors are really going up as the distance from the center of the image or the radii is increasing. So we can definitely see that this model is insufficient to calibrate this camera. And we've actually been working with the companies who've been using this camera for mobile mapping system or applications like this, and they've had problem with the matching their point cloud to these images with the model that was given by the company, the central perspective model. But when they use the fisheye model, then all the errors and mismatches between the point cloud and the images got corrected. So the other part of the calibration is, of course, system calibration. So whenever you have multiple sensors in one system, you want to know the relative orientation parameters between your sensors, or basically the bore sight angles and the lever arm offsets between the sensors. So I just give you an example here. This is a system that we built out of a laser scanner, and here I will just turn my laser pointer on. Yeah, okay. So based on a laser scanner and a camera, and there is an INS in there too. Adding the camera was both for collecting, of course, spectral or optical information, but also it makes the calibration process much easier. Calibrating the LiDAR and an IMU is more difficult than calibrating the camera and the IMU, just because that frame nature of the images we take with the camera. Similar to that, we can, instead of calibrating the LiDAR directly to the IMU, calibrate the camera and IMU during the flight. And then you're in an offline procedure with enough ground truth data. Like in this case, we've had a lot of planar objects at different directions and orientation in quite a large room, like a room of 7 by 7 almost. Meters of size, we've been able to calibrate the camera and the LiDAR with respect to each other. So that would actually make whole calibration process more easy and avoid looking for specific features like planar features during the flight, on the flight calibration. So here we can see this type of calibration will leave us with a lot of equations, because every single point that is observed at a different station by the LiDAR will add equations into our equation system. Cameras and their images will also add equations. All the features that are visited in the camera will also add equations. So we ended up with more than 1 million equations to solve. So that meant we had to do something with the bundle adjustment process. And that's why we've developed a very sparse bundle adjustment that can handle millions of equations at the same time. So that would allow calibrating the system. And now that we have the systems ready, we can actually go to the real work. So here is an example of how I don't know if you see it in video or not, hopefully you are. So an example of how 3D visual perception can be done using drones that have multiple sensors. We've been very active in sorry, I think there has been a problem with my presentation here, trying to. Okay, hopefully you can see the slide I'm modifying to speed up because I don't see it anymore on my second screen. I don't know how I can even receive your comments. Hello? Okay, so I'm just assuming that everybody can still hear and see everything. So we've done a lot of work in also modifying structure from motion algorithm to make them faster. For example, one of the time-taking steps of structure from motion to create dense point clouds is the high-density matching or dense matching. We've been working on different techniques based on intrinsic curves to speed them up, and actually our approach was considered as one of the most accurate and the fastest algorithms on a middle blur stereo evaluation benchmark. There are sometimes needs to improve the data and do like data processing before getting into the structure from motion step. For example, removing the shadow so that the result can be both actually can be made. Sometimes the shadows are so intense that we lose all the features between images and we cannot really match images against each other. By removing the shadows on an image-based level, we can actually create a better perception of the image and also make the structure from motion process much better, easier. We've been using perception or visual perception for navigation purposes as well. We've been using other types of perception, not just based on region, but also based on range. For navigation, for example, in this setup, we've integrated ultra wideband radio frequency sensors on our drone. So that ranging using multilateration, pretty much similar to the concept of the GPS, for example, but on the ground to navigate our drone indoor, and whenever there is not enough GNSS accuracy in any kind of GNSS degraded or GNSS denied environment. Here are a few examples of my laboratory using drones for human machine interaction and doing VR or AR. We've also integrated a camera on this small drone, and it's and the only sensor it has is a camera. It doesn't even have an IMU. We've been using this for doing. We've been using this for. Sorry, just. We've been using this for exploration of the environment. So for example, in the video on the right hand side, we've trained this drone actually to identify the tripod, and it's doing all of this by itself actually. So whenever it identifies this object, it tries to explore it, take enough images around it so that it can build its map in 3D and do that kind of exploration around unknown objects. We've been using camera-based or vision-based for georeferencing LiDAR data as well. So the system I showed you that had a LiDAR and a camera integrated. Here we show what would happen if we had used the GNSS-INS for determining our trajectory and thus for georeferencing the LiDAR data. and what would have happened if we had used the camera-aided INS integration. So the accuracies are, given that the GNSS that we were using wasn't even an RTK GNSS, so we are thinking, we are talking about meters of change in accuracy. So here we can see that system in action for actually precision agriculture applications. So we built this map of the environment by integrating the LiDAR data to build the 3D DSM, and then using the images to build the orthophoto. So it's quite a fast process because it doesn't need to go through all that photogrammetry processing anymore. The good thing is that also integrating this 2D image information and integrating the 3D laser scanner information, we can also use them for different tasks like vegetation detection and ground filtering applications. So whenever the microtopography of the ground is needed, we can easily use a combination of features extracted from 3D and 2D to be able to identify all the vegetation, remove them, and keep the soil to calculate the microtopography. We've done quite some work on miniature multispectral camera, like maybe work with the MicaSense Red Edge or Altem cameras. They have these different cameras shifted with respect to one another to create multi-band images. Of course, if you look at the images, original images, and you try to just create composite bands out of them, it will be impossible because, as you can see, the images are shifted. The cameras are shifted with respect to one another, so it will be the images. One of the ways that the manufacturers suggest correcting this is using a simple shift, so finding the best shift between the two images. So of course, that's not a very good solution because we are, this image has a 3D nature behind it, so you cannot just shift the two planes and assuming they will fit. The other solution that also their open source software supports is homography-based matching or co-registration of the multi-band images, which is usually working well if you're, for example, keeping a constant distance from the ground, or like so that, or you're far away from the ground or from the object, so that the objects on the ground can be considered as a plane. And then, of course, homographies are plane-to-plane matching, right? So that would work. But in this case, you can see it works. If you fit the homography based on the ground plane, then it works very well for the objects that are on the ground. But for these objects that are not on the ground, then you will have a mismatch between the objects. What we did was actually a technique that, first of all, doesn't need feature matching, because finding features between two images of different bands is a little bit difficult. What we did instead is performing the very accurate relative calibration or boresight and lever arm offsets between the cameras in the camera system, and then do a dense matching between the two nearest bands of the cameras, and then kind of expanding the results of that matching to all the other bands through trifocal tensors. So it's all mathematics. There is no more matching. So it doesn't matter that, for example, the red band and the green band don't have any overlap in terms of spectral information. So that would allow matching on objects that are far, close, whether they are on the ground or not. You can see that the composite layers or the multiband layers do co-register very well. Another application of these cameras, so here we can see an outcome and a small RGB camera on this drone that we've used for plant counting. So it's not very obvious in this zoomed out orthophoto, but this is a leek farm. So we've been trying to, at the very earliest stage of their growth, but they are almost looking like spring onions. We've been trying to count them so that the producer has a good idea of the year's yield. So quick look in the middle, we've been using regression networks for counting these objects, but because they are not really that much of complete objects to be individually detected. You can see like here, they are really looking like, even like human eyes has difficulty to distinguish between these plants, and we've actually used farmers to annotate the data because you cannot tell the difference sometimes between weeds and real plants. So the result of that regression network is a heat map or a density map, heat density map, we can say, through which we can then do more processing and get the counting. So now we can actually count every single object. Another application with the same camera, we again tested on the leek farm. It's quite interesting at a different actually level of growth. This time plants are pretty much into one another because they've become much larger. They've grown quite much. So they are interested in leaf level temperatures of these plants, but we all know that most of the thermal cameras that we can use with UAVs are quite low resolution. So if we want to extract the plant from that thermal camera, it's almost impossible. So what we did, we used the near infrared band of the multi-sensor camera to detect the plants and then project it back to, using the technique that I just showed you, we could simply project it back to thermal images. So to do the semantic segmentation of the leaves of the plants, we used an encoder-decoder network, CNN network to do that. And then here is the result of projecting the leaves back to the thermal camera and then up to the, putting it as a layer on top of the digital surface model. So we can see, actually it gives quite good insights to the farmer. So the farmer noticed that the topography or the microtopography of their field is not well organized. For example, we are higher in the elevation here, so all the water would drain out and go to this part where has considerably lower elevation. And so we can see the plants in these areas, they are quite in good health because their temperature is normal. But the plants in this area, they are close to being dead because their temperature is showing to be too high. So this type of information can help farmers decide quite well how to manage their farm. We're using also, we all know that using the height of the plants, we can kind of predict the yield for different types of crops. And then we've used this we've collected this type of data over years. And then we've used predictive analysis based on recurrent neural networks to be able to say whether what's going to happen in the next year in terms of yield. We've been using drones a lot in civil engineering applications, specifically for structural health monitoring and infrastructure inspection. So here is an example of using drones for telecommunication tower inspection. So not only the aspect of 3D reconstruction, we've built this software where they can actually measure objects on 2D and we would reproject it on a 3D CAD. And also certain components of the system that they are interested in, we are detecting them automatically. For example, on these antenna components, they have to be able to read the text and then enter it into a report so that they know which antenna has been inspected. So we've been doing this optical character recognition, text recognition as well. This is another project mainly on energy optimization. So we've been using orthomosaics of the city to extract the building rooftops. And then from there, we've been doing calculation based on the position of the sun, the geometry of the rooftop to be able to estimate how much of energy will be produced at each rooftop if they had They had covered the surface of the rooftop with solar panels, and this was a project with NMAX, an energy provider in Alberta. We've been working on damage assessment and infrastructure inspection using drone-based vision technologies. So here is an example of again, a type of semantic segmentation neural network that we've used for automatically detecting the cracks. And we've been using a stereo vision to be able to also reconstruct the cracks, or accuracies are in the level of 0.1 millimeter in terms of 3D reconstruction, and over 90% accuracy in terms of pixel-based crack segmentation. This is not, we haven't taken this on drones yet. It's been on the first phases of testing it just by a shaking camera, basically. So the camera is equipped with an accelerometer itself, so that the movements of the camera can be measured, and then it's looking into infrastructure that is either deforming or vibrating. And then we've been able to extract the movements and the deformation of the structures as precise as the laser transducers and the accelerometers attached to the structure could do it. We've used drones in intelligent transport systems. So here's a new roundabout that they've built in Calgary, and they wanted to know how the traffic is actually moving around this new structure or road structure. So for, I think, 2 days, complete 2 days, both morning and evening, the drone has been up moving different sides of this roundabout and have been collecting the data. And we've been tracking cars both in 2D and in 3D through the roundabouts. And this is another project in a similar application in Toronto. And we've been able to actually track the cars in terms of their position and their speed over time. So a video of the speed of the all the cars from top point view. So all the like in this case, all the 3 roundabouts, they have their information at the same time, so that the city can decide whether that was a good decision to build this road structure, how the cars are behaving, do they need to put also stop signs and stuff like this, or already the speeds are correct or not. So we've been using different types of cameras, as I said, also hyperspectral cameras. For example, we've done macroalgae classification using hyperspectral images, both for environmental studies, and also algae is now a commercial product in Canada. So they are eatable. So they've been looking into the yield of the different types of the microalgae and see how much commercially they can benefit from them. We've used also drones in wildlife management. So again, combination of thermal and optical cameras to be able to detect individual, if you use this information and to detect individual animals that different managers are interested in. This is not really drone as in like airborne drone or flying drone. It's more a surface drone that we've been using for seabed and riverbed mapping. We've done projects also in the Arctic for Arctic seabed mapping using this system. So it's kind of a different level from the ground and not from the air, using unmanned systems for mapping. So I want to thank all the agencies that have funded our research projects. Of course, there are many, many industries involved in these projects that I can name all of them, but big thanks to the funding agencies in Quebec, in Alberta, and in Canada in general, who supported our research. And now I want to just take a, I think I've already passed my time, but I will take just a minute to talk about Journal of Unmanned Vehicle Systems. I'm a co-editor-in-chief of this journal, and as you know, we are the media sponsor of the conference as well. So all of the presenters who are interested in expanding their research work and submitting it to JUMS, they are welcome to do that to a special collection that we've assigned and dedicated to this conference. It's a great pleasure to collaborate with this conference for the first time, and hopefully in the next years as well. Publications will be free. And we have quite a high index of H index of 19 or H5 index of 32. So published with Canadian Science Publishing. So please, if you're interested, go ahead, submit your work to JUVS. You have until mid-October to do so. Thank you so much. If you have any questions, please contact me by email. I would be more than glad to help you out.
Thank you, Dr. Shahbazi, for this insightful presentation. Your work is indeed very interesting and engrossing. And we'll look forward for collaborating with you in future. Right now, we have received a few questions from some of our viewers. I'll read it out for you.
Yes, please.
There is a question from one of our research scholars. He asks, for data fusion, do you use any open source algorithms or some in-house developed software?
Yeah, we mainly do in-house, of course, whatever open source software we can use to integrate in it, we can, whenever it's possible, we will do. So for data fusion, like if you're talking about the multispectral cameras, it's an open source software. Actually, if you go to my LinkedIn, the link to the GitHub of some of these projects you can find through my LinkedIn posts as well. Specifically, this co-registration of multi-band cameras, the whole source code is now available to the public. Yeah, so most of it is either open source originally or made open source through our in-house developments.
Okay, another one comes. You have shown a graph comparison for camera calibration parameters for wide angle and fisheye lens. So in what conditions do you recommend to use fisheye lens for better consistency in performance?
Yes, it's a very good question, because after that, so it always comes down to whether trusting the manufacturer or not, and whether to test other models than what the manufacturer proposes. And it's happened actually 2 times to us so far. So Ladyboy camera is the one that we thought it should be a central perspective, but finally the fisheye model was working better. And then the second one, I don't know if anyone has here worked with the Z stereo cameras. So the proposed model by the manufacturers didn't work either. So we had to come up with a different model. So I think a quick answer to your question would be experiment different models. If you're doubting whether it's a real wide angle or a fisheye or other models, experiment with different models and see actually which one is going to perform better in your on your data. I can't have really a global answer for that.
Okay, ma'am. Another question from another research scholar from our lab. He's asking, we get very few points on the leaves and vegetation. In case of even small winds, we would get data redundancy of the leaf winds. In that case, how would you differentiate points as noise or points as vegetation?
So the good thing is that you can, when you have the camera, then you can also count on the spectral information. So in the case that I showed you, we've done quite some pre-processing actually to get to that point cloud. So we've done, because our results of georeferencing the LiDAR hasn't been so accurate just because of the drift of the GPS INS and then the drifts of the camera-based INS integration as well. So we had to do some post-processing using feature tracking and matching in the point cloud itself to make sure the point cloud already was at high accuracy. And then now actually assigning colors to the point cloud from the cameras would be good because the parameters of the camera to LiDAR are accurate and we can use it to give color to the points. And at this level, we can actually detect objects that don't really represent either ground or vegetation, and then remove them first, and then from what is left, do a vegetation removal. So I would say a pre-processing the point cloud plus removing all the objects that do not represent vegetation.
Okay, ma'am. A quick last question from one of our viewers, Mr. Utkarsh Ahuja. He says, what factors were you able to collect for cell phone tower inspection?
For the telecommunication tower, I didn't get the whole question.
Yeah, he's asking, what factors were you able to collect for cell phone tower inspection?
Oh, so like what aspects of the telecommunication tower? So they've been interested in if there have been any movements from its original. So we had the as-built structure, position and orientation, and also the orientation of the antennas. Each of the antennas on that tower, it's interesting to them to know where the antenna is headed. So one of the objects that we detect actually automatically are the antenna surface. And then back projecting that to the 3D space, we can tell what is the orientation of the antenna. So that's one thing that the telecommunication tower is interested in. The second thing is that ID of the antenna. So each of the antennas we inspect, we have to know which antenna it is. So text recognition would allow that. And then the tower itself. So even every single bolt on the tower, they want to know whether it's moved or whether it's still intact. So detecting the bolts on the tower itself is another thing they were interested in. So I hope I understood the question correctly and I answered it well. If not, please email me. I'd be more than glad to help you out and answer more precisely.
For any further queries, our viewers can directly contact ma'am. The email ID is displayed as on your screen. Thank you, ma'am. It was indeed great to hear from you. And I also thank our online audience. I also thank our online audience for being a very patient and keen audience. So with this, we end the keynote session 7 of today and hope to see you all tomorrow morning at 9 a.m. Thank you.
Thank you so much. Bye-bye.